Hello guys, so you're welcome again. So in the last lecture we were looking at the properties of the matrix exponential. Alright, and then we looked at the first few properties. We said e to the a multiplied by 0 is e to the 0 cos I, and e to the power a multiplied by t times I is equal to e to the at multiplied by e to the as. C is very important. You see a comment on that in the next slide, that the matrix exponential has an inverse, and to find the inverse of the matrix exponential, all you do is replace t with negative t and you have the matrix exponential. Also, if you have e raised to the power the sum of two matrices multiplied by t, then you can separate it out, right, as e to the at multiplied by e to the bt, provided that ab is equal to ba. All right, this one will be easy to prove. You have e to the power rit is equal to e to the rt multiplied by I. Okay, and if you find the derivative of the matrix exponential, you get a multiplied by the matrix exponential. Okay, we're going to prove this actually in the next slide, so that's easy. So this was a remark about the inverse of the matrix exponential, which I've already made. Now, to find the derivative of the exponential, all you do is plug in the definition of the matrix exponential here. Okay, so you have ddt of, this is from the definition of e to the at. Find the derivative. This is just a constant, so that's a zero matrix, so it doesn't appear. Differentiate this with respect to t, and you have a. This will give you 2t all over 2 factorial, and you have a squared. The 2 from t squared cancels out this, so you are left with a squared times t. Do the same for the rest. In the next line, you can factorize a out, and you have I, right? A times I is a. And then over here, you are left with at, you have a squared t squared over 2 factorial, and so on. All right? And now what you have in the square brackets here is just the definition of the matrix exponential, or is the matrix exponential. So this is just equal to a multiplied by e to the at. So that is the last property that we looked at. This implies that x of t, x here is of course the solution of the system. X of t is equal to e to the at. It's a solution to the matrix differential equation this. All right? Because when you differentiate this, you get a right hand side. It's this. E to the at is x. All right? So this implies that the matrix exponential is actually a solution to this matrix differential equation. So that is important. All right. Now, since we have just shown that the matrix exponential has an inverse, it's invertible, and it's a solution to the system, it implies that the columns of the matrix exponential, the columns of this, are linearly independent solutions of the system of equations, which implies that the matrix exponential is actually a fundamental matrix of the system of equations. Okay, in a fundamental matrix, the columns of the matrix, okay, form solutions. Okay, they are linearly independent solutions of the system. You have to go back to chapter 3 in the new lecture notes. If you look at chapter 3, you will see the definition of what a fundamental matrix is. But it's important later on in solving systems. So this theorem summarizes that if A is an n by n constant matrix, then the columns of e to the at form a fundamental solution set for the system. Thus, and therefore e to the at is a fundamental matrix for the system, and the general solution is given by this. So once you find your fundamental matrix, you just have to multiply it by this constant c vector, and you have the solution to your system. That is why we are learning how to we are going to learn how to compute the fundamental, the matrix exponential, because once you have it, then basically you have a solution. All right, good. So I said that looking at the definition, it's difficult to compute the matrix exponential directly from the definition. It's quite involving. But if the matrix A is a special matrix, a special type of a matrix like a diagonal matrix or a nilpotent matrix, okay, then it's relatively easier to compute it. So we're going to look at the diagonal matrix, and then later on in the next lecture we'll look at nilpotent matrix, and then generalized eigenvectors. Okay, so for the diagonal matrix, if I have a matrix A which is diagonal with R1, R2 up to Rn along the main diagonal, then to compute the matrix exponential, all I do is that I multiply each of these elements by t, and then I raise them to the power e, or I take e raised to the power, all these diagonal elements multiplied by t. So you get that. So that is relatively easier. Okay, much easier to compute. So here's an example of a 2 by 2. So we are actually going to do this using the definition. So you have a matrix A which is S0, 0, G, so it's diagonal with elements S and G are not 0 along the main diagonal. Okay, then by definition you have e to the at is given by this. So all we need to do to compute the matrix exponential is plug in the identity matrix, which is easy in this. This is just 1, 0, 0, 1. We know A, we need to find A squared, A cubed, and so on. Now A squared will just be A times A. Multiply this out, you get S squared 0, 0, G squared. You find A cubed will just be A squared times A. A squared we just computed is this. A is this. Multiply them out and you have S cubed 0, 0, G cubed. Now if you follow this, you see that by induction A to the power n will just be S to the n and G to the n along the diagonal. Similar to this, A squared is S squared, G squared. A cubed, you have S cubed, G cubed along the main diagonal, and you have this. So you plug all this back into the definition. Okay, if you do that, you're going to get this relation here. You're going to add the matrices. All you do is add the individual elements. So 1 plus st plus s squared t squared over 2 factorial and so on, and you add these terms, and then you get these. Okay, note that this 1 plus st plus s squared t squared over 2 factorial plus this to infinity is actually the definition of the exponential. So all of this is the same as e to the st. This is 0, of course, that's 0, and this is e to the power gt. Okay, so if you just have the matrix S and G along the main diagonal, if you use that definition, you can prove that the matrix exponential is given by this. Okay, so that's kind of straightforward. Just following on this one, this is an easy example following that. If I have a system x prime is at, where a is given by this is a diagonal matrix. So the matrix exponential is just given by, I multiply this by t and have e to the power negative 2t, e to the 3t along the main diagonal. And the solution will just be the matrix exponential multiplied by a constant. Okay, that's multiplied by a constant, which you can split as this, and that gives you the solution. All right, so that is relatively easy, and so you can look at these exercises. This is the matrix we just considered. We just solved it. So the exercise here is for you. This is for your understanding. For you to take a look at find the solution of this system by finding the eigenpairs, eigenvalues, and eigenvectors. Also, you can also solve it because it's a diagonal matrix. You can actually split this system into individual equations and solve them, if you like, x and y, or x1, x2, and solve them. So see whether the solution you get is the same as the solution we have here. Okay, and then solve the system. This 3 by 3 matrix. It's a diagonal matrix. You want to find the matrix exponential. Okay, so try your hands on that. That should be relatively easy as well. Okay, so we've looked at the diagonal matrix, which is a special type of a matrix where it is easy to compute the matrix exponential. The next one we'll look at the nilpotent matrix, and then we'll look at other ways of computing the matrix exponential. Okay, all right, so I'll see you in the next